We've all had that frustrating moment where a website completely freezes up on us. You click a button and the whole page just grinds to a halt. When that happens, it usually means a microscopic conveyor belt inside the code has jammed. This graphic shows how that code normally operates. By default, JavaScript is a very straightforward machine. It reads and executes your instructions in a strict, straight line, moving from top to bottom and left to right. Looking at this diagram, you can see why JavaScript is single-threaded. It lacks the ability to multitask, processing only one command at a time. Every new task waits in line. The thread cannot move on until the current instruction is completely finished. If code could only ever run in that one rigid straight line, building complex programs would be impossible. To handle real-world tasks, we need mechanics that allow us to pause, branch out, and bend that line. This grid breaks down the 4 main ways developers direct traffic. We can bend the execution thread using conditionals to fork the path, loops to create roundabouts, jumps to teleport the thread, or functions to run separate subroutines. Let's focus on loops. Here we see the engine of a standard while loop. Notice how it acts as a gatekeeper. It checks the condition first, and only if that condition is true does it allow the thread into the repeating execution block below. By contrast, this diagram illustrates a do-while loop. The architecture is inverted. The execution block sits above the gatekeeper, meaning the engine runs the code first and checks the condition afterward. This guarantees the code runs at least one time, no matter what. A for loop is mechanically identical to a while loop. It simply packs the start, condition check, and counting step into a single line. The thread cycles through these identical steps, automating work until the exit condition is met. Loops give us a tremendous amount of automation power. But requiring an exact exit condition introduces a severe risk to our programs if they aren't managed perfectly. This warning schematic shows a common developer error, the infinite loop. If you forget to include the command that changes your condition, like a missing number incrementer, the exit requirement can never be met. The condition gate stays permanently locked. The execution thread is trapped inside, spinning endlessly until it consumes all memory and crashes the browser entirely. To prevent disasters like that, we use jump statements. This map shows the specific exit commands developers use to instantly pull the execution thread out of a dangerous structure. Looking closely at this illustration, you can see how the break command operates. It acts like a pair of scissors, immediately severing the loop and transferring control directly to the normal code waiting underneath. This comparison demonstrates another critical use for break inside a switch statement. Without a break command, a switch suffers from fall-through. It blindly executes every subsequent block of code below it, like water flowing downstairs, even if the values don't match. There are a few other handy jump commands, too. A continue statement acts like a skip button to instantly jump to the next round of a loop, and a throw statement acts like an emergency flare, blasting the thread straight out to your error handling logic. Whenever you build automated logic, these jump statements serve as your definitive safeguards, ensuring that repeating code never destroys your application's stability. But real-world applications aren't always so simple. Often, you will need to search through complex data by placing one loop completely inside of another, creating a deeply nested architecture. As this diagram shows, a standard break statement has a limitation here. It only ejects the thread from the immediate inner loop. That leaves the thread stuck spinning inside the wider outer cycle. To solve this, developers use the label syntax shown here. A label is just a custom reference name, followed strictly by a colon, that you paint onto a specific block of code so the engine knows exactly where it is. By combining these two tools, pairing a break command with that specific label, we create a targeted escape hatch. As seen in this graphic, the thread instantly blasts out of the entire nested structure, landing exactly where you told it to. By stringing loops, conditionals, and labeled jumps together, we gain total, precise directional control over JavaScript's single execution thread. But even with perfect control flow, the system still has a major weakness. It can't handle heavy cargo without stalling. Imagine your perfect loop requests a massive, slow-moving file from a remote server on the other side of the world. That request lands right on the execution thread. This diagram illustrates the resulting bottleneck. Because there is only one thread,
That slow task physically blocks everything behind it. The entire application freezes, and the user interface becomes completely unresponsive. To keep the application running smoothly, we use the architecture mapped out here: asynchronous execution. This mechanism takes heavy tasks and temporarily offloads them to a bypass track, keeping the main assembly line moving freely. Mastering your basic control flow is the necessary first step in writing robust code, but learning to build these asynchronous bypasses is what makes modern, lightning-fast web applications possible, and we'll dive into exactly how to build them in the next lesson.